Hi, I'm John Green. This is Crash Course Big History. Today we're going to be talking about the formation of the solar system approximately 4.567 billion years ago. 4.567. Could that possibly be a coincidence? Yes. So if you weren't asleep during like every minute of grade school, you're probably familiar with the basic layout of the solar system and the 8, formerly 9 planets. What you may not know is how the planets fit between the stars and life as the linchpin of rising complexity.
Mr. Green, what about Pluto?
Oh, me from the past. I know people like to root for the underdog, particularly when the underdog shares a name with Mickey Mouse's dog. Off topic, but how come Mickey Mouse has a dog who is a dog and also a friend, Goofy, who is a dog? But just remember that Pluto also shares a name with the Roman god of the underworld, who was very unlikable. But regardless, the word planet is a man-made classification for a natural phenomenon. We use it because it makes it easier to do science. Pluto hasn't cleared the rocks within its neighborhood orbit like planets usually do, and there's even a dwarf planet on the edge of our solar system, Eris, that's bigger than Pluto. And there are hundreds of others that are comparable to Pluto. The nature of the universe has not changed. It's just that we learned that Pluto was not acting like a planet, so can we please just drop the Pluto thing? So we're now moving from the scale of galaxies, which involve millions of light years, to a neighborhood that's only a few light hours from the Sun to Neptune, the farthest planet, or at most a light year or two to the distant Oort cloud of billions of comets held by the gravity of our Sun. So last episode we talked about how the stars are like our great many times over grandparents. Well, our Sun actually had stars as its parents too. It's most likely a second generation star, which means that the Sun was formed from the wreckage of previous dead stars, and that it contains elements other than just hydrogen and helium, heavier elements that are forged in the bellies of stars, and some of which are like flung out by supernovae. When our star formed, its immense gravitational pull sucked in 99.99% of all the matter in the solar system, so in this case we are all the 0.01%. But essentially the rest of the solar system is made up of the debris, like the crumbs, the dregs in the bottom of your coffee cup. Our Sun formed over the course of about 100,000 years in what's called a solar nebula, which is like a fiery cradle of wisps of dust and gas. Then the solar nebula began to compress into a star, probably triggered by a nearby supernova that also, usefully, peppered the solar system with even more heavy elements. And then as the Sun slurped up like almost all the matter in the solar system, pressure made the core of the Sun heat up and it came to life. The usual fusion of hydrogen and helium began to happen and continues to happen, which is nice because otherwise the Earth would be extremely cold and also very dead. So how do we know all of this is true? Well, let's talk to Emily from the Brain Scoop.
Well, a good piece of evidence is the construction site rubble from that time. Meteorites form a sort of fossil record. Meteorites fall to Earth, and some of them are primitive clumps of nebular dust. Careful investigation reveals them to be around 4.568 billion years old. The point is, there can only be two environments where iron-60 came from. One is inside a very old giant red star, and the other is within a supernova. Elderly red giants move away from star-forming regions in the galaxy. Chances are the Sun wasn't formed near one of those. So it's much more likely that our Sun's formation was triggered by a supernova blast.
So in the early days, the heat from the Sun blasted lots of gassy materials away from the inner regions of the solar system, encompassing Mercury, Venus, Earth, and Mars. Further out, in the vicinity of where Jupiter is now, it was cold enough for volatile gases to hang around and even become liquids or solids. That's why the inner planets, like us, are rocky, and the outer planets, Jupiter, Saturn, Uranus, and Neptune, are all these humongous gas giants. So what happened to the remaining 0.01% of our solar system, and what does this have to do with the rise of complexity? Well, the dust floating around the baby solar system wasn't just elements. Like heating in the stellar nebula allowed this dust to sometimes form more complex configurations of elements, like for one thing, around 60 different kinds of minerals. So then the dust began to stick together. Why do I have balloons, by the way? Well, obviously I'm going to tell you shortly. So you may have noticed that if you rub a balloon onto your head for long enough, it will stick. That's because of electrostatic forces, precisely the same forces that allowed the dust in the solar system to gently gently collide and stick together. And then as those clumps of dust got bigger and bigger, the collisions ceased to be so gentle. So within 100,000 years, there were many objects of up to 10 kilometers in diameter in the solar system, and the force and heat of those violent collisions allowed the formation of still more celestial bodies. Objects continued to collide, the larger objects sucking in the smaller ones with their gravitational nets, and then the largest in each orbit began bulldozing its way through the remaining material. So after about 1 million years, the solar system consisted of a few dozen or so protoplanets. They were roughly between the size of Mars and our moon, and then over the next 10 to 100 million years, the game of pool continued, each collision being something terrifying to behold, until we wound up with the 8 massive planets we are familiar with today. But of course, there's more than just planets in our solar system. There's an asteroid belt between Mars and Jupiter, for instance, which may be a failed planet messed up by Jupiter's gigantic gravitational pull. And then on the edge of the solar system, there's the Kuiper belt, a region of planetary shrapnel like poor old Pluto. And even further out in the boonies, there is the Oort cloud. It's like this huge borderland teeming with billions of comets, but it's still within the sun's gravitational pull. And the Oort cloud is a light year away. That's how massive our sun is, and it's a pretty